All right, we should get started. Somehow it got to be time already. So we have one more week before spring break. Everybody looks like they're ready. Looks a little tired. Maybe it's just me. Maybe I'm projecting. No. We're gonna move on to visual perception today, which is for us gonna fall under our discussion of the wave senses. Recognizing, of course, that light can be characterized as waves or rays or quanta, if you like. And all of those ways of dealing with light actually do play a part in the story of visual perception. We are going to focus mostly on the wave aspect because it has to do with color vision. But if you wanted to talk seriously about things like luminance, we would talk about photons impacting, and that would be in the quantum consideration. So we'll talk about it as a wave sense and we can do that without any harm. Your visual sense. Let's see if I can make this work. Is an amazing biological evolutionary accomplishment. It is absolutely top-notch. It's one of those things that's so wonderful and specialized and fine to the point where you just can't imagine how it would be any better. That sometimes it's used by people arguing against evolution because it's just like what the steps would be that would allow you to more or less accidentally, right, through the dynamics of evolution, discover such a precisely and beautifully organized mechanism. Just doesn't seem possible. And yet somehow here it is, and evolution is the best explanation we have for its existence. But it is really quite incredible. And the more you go into it, the more you realize that it is wonderfully specialized. So what we're going to do is kind of skim across the surface. If you take the course in sensation and perception, which is over here, got a lot more about it. It turns out there's everything that every category we're gonna talk about goes 3 layers, 5 layers down, right? So there's a lot more complexity here. So again, we're just gonna kind of stay on the surface level. So your visual system is attuned to pick up a very small window, very small pocket of the electromagnetic spectrum. Right? So there's really no other than that, it seems like to us that this is where vision resides. There's really nothing special about that pocket. It's just that that's where our visual system happened to get tuned up. And so we are in. I have trouble with Unity. I guess we are. Oh, I could turn it on. That would be how I make it work. Most things like to be on before they work. Maybe that'll do it. Yeah, that does it. Okay, here we go. So this little rainbow area here, which will make the rainbow make a lot of technical sense in a second, right, is the area out of the larger electromagnetic spectrum, which you can see is given by the power here, right? So way up here we have AC circuits and AM radio, and way down here we have gamma rays and X-rays. And what you can see, the visible spectrum, is here. Just in this little niche here. And everything else you can't see. It's not that somebody couldn't make such a detector, installed it in your visual system. They could, but they didn't. And so what you get is this, and it goes from 400 to 700 nanometers in wavelength. Wavelength is the alternative way to talk about frequency, essentially. So it is a measure of how often the waves are cycling. And I'll give you a graphic on that in 1 second. So for us, the wavelength of light generally corresponds to hue. Talk about that more too in a moment. But that's one of the reasons we talk about wavelengths in particular when it comes to vision. So the point to appreciate from this slide is things could have been otherwise, biologically speaking, and for other creatures that have visual systems, things are shifted up and down a little bit, right? Just like they were in the auditory system, if you remember. But this is it for us, 400 to 700 nanometers. Outside of that range, you can see. So let's talk about the properties of waves that are kind of translated into your visual experience. One that we've already discussed is the amplitude of the wave. If you remember, is the height of the wave relative to the zero marking, right? Which is given by this line here in the center. All right, so that's the amplitude of the wave, and that corresponds roughly to brightness in much the same way that loudness corresponded to the amplitude from the auditory system. So there's an analogy to be made between the brightness of the visual experience and the loudness of an auditory experience. Maybe that hopefully makes some kind of intuitive sense. The wavelength, of course, like the frequency, is about how often the cycle repeats. Here now measured just by the peak to peak distances. So we talk about 400 nanometers. The nanometer difference between peak to peak would be 400. Okay, so when we talk about wavelength, that's the quantity we're after. So if they were further apart, right, the wavelength would increase, closer together, decrease. Okay, so that's what we mean when we talk about wavelength. All right, I see some looks of concern and confusion. Questions on that? No? Yes? So they could have done frequency just as easily. They just went with wavelength. I think probably for historical reasons. As I said on the last slide, wavelength corresponds to different cues for us. So if you have one really dominant wavelength, things tend to be seen as being that color. So reflecting back off. For example, these lovely chairs here, I don't know if you can all see the chairs, right? Kind of a nice burnt orange. So what's reflecting off of here is predominantly in that orangey kind of region, all other things being equal. We didn't talk much in the auditory system about this other kind of messiness, which we can think about as complexity or timbre or something like that. And that has to do with how much mix there is in the waveforms. So here, right, we're in this beautiful situation. It's just a sine wave. There's just one of them. It has a particular wavelength. It's like pure and simple, and that's very nice. But the world actually doesn't much come that way. It would be very unusual to have such a thing happen. Nice for explanatory purposes, of course. But what actually happens is even worse than what is shown here, which is there'd be a lot of wavelengths all coming off at once. And that mixed together is, in the parlance of visual perception, known as saturation. So things get more and more complex as they become more saturated. So we can think about that as complexity or purity a little. So let's talk about it as complexity. Complexity is good. We won't have much to say about that. You should know that it's out there and that almost everything you're seeing has a reasonable degree of complexity to it. Right, so this is very gentle introduction to the, I don't even really want to say the physics of light, right? It's just sort of basic facts about what light, how light is measured. And what happens when these 2.5 kind of parameters are discussed: intensity or amplitude and wavelength, right? And then the half one I'm thinking about is sort of complexity, like how many of the waves are there. Let's push on. So here's a cutaway of the eye, and we're just sort of going to warm up to the idea that we could appreciate its structures. So just like the ear, we want there to be gathering and focusing parts. The ear does a more modest job of focusing. The eye is very explicitly focal. Right? But we want to be able to gather in the light and focus the light. And then we want these, what we'll call translating parts, where we have structures for transduction, right? And then, of course, we want to send some signals up to the brain, where some relatively inexplicable things are going to happen. At this point, everything is going to appear kind of right in front of you on a plate, essentially. Right? You get to the brain, things will be much more mysterious. But the beauty of this is that we can actually see these things in these simple diagrams. The anatomy of the eye does a lot of this stuff. Right? So we're going to talk about on the next slide structures for gathering and focusing, and some of the structures that do the transduction. So hopefully this is obvious, right? We've taken you've probably seen many of these sort of images. We're cutting this in half. Right? We have, start here on the outside, we have the cornea. We have the iris, which are just muscles here. We have a lens, a literal lens, with more muscles for bending it. At least for you guys, it still bends once you get past 50. Bad news, lens doesn't really bend anymore. So all that accommodation stuff that was able to make things focus on your retina, the back here, doesn't really work anymore. Not good. So here's the retina, which is where all our photoreceptors are going to be. We have the optic nerve going out here. We have a blind spot that I'll explain in a moment. And of course, the fovea, you've probably heard of that before. Oh, and the pupil here, I think I skipped the pupil. The pupil is just literally a hole in the iris. So I've probably now just stolen all my own thunder from the next slide. But anyway, we'll do each one of them in turn here. So the cornea is this outermost thing. It does business. It actually is involved in the refraction of light. And there are some procedures that you can have to help with nearsightedness and farsightedness of the usual kind, right? So, the sort of things you would usually wear glasses for, that actually are slight shavings of the cornea to slightly change its refraction. And rather than address the lens directly, they just address it at the corneal level, because it has like a particular contribution to refraction that's unchanging, right? It doesn't the cornea doesn't accommodate the way the lens does. So it does do a little bit of bending of the light, focusing of the light. It's clear and it's pretty tough. You don't want to scratch it, but it can resist a little bit. It is, right in contact with the air. The iris, which is not, the iris is sort of the most beautiful part of your eye. Not very beautiful in this diagram, right? But it's the colored part of your eye. It's actually a muscle. Isn't it nice that, you got a muscle that's colored? It could look like, a piece of roast beef or something, but it doesn't. It's beautiful. So you have your iris here, and that's actually making, as it contracts and expands, it is changing the pupil size. Okay. The pupil is just a hole. It gets its own name. You don't usually name holes, but this guy is important and is very prominent, right? It's a hole. It's that when I look into your eyes, I'm actually looking into that hole. And that's nice, I guess. So that hole, of course, is particularly important because that hole and its size determines how much light gets into the eye chamber. And that's where all the business is done. So it's an important bit. The lens, obviously, seems like would be an important thing to have. So the lens is focusing the light very precisely onto the retina back here. And you actually are bending it using muscles that are being controlled by the ciliary body. And that slightly changes the shape of the lens, and of course then changes the how far the thing can be that will now reside in nice crisp form on your retina, essentially. And hopefully that all squares with your prior understanding of this, although maybe some of this isn't. I don't know. So here, this little kind of piece here, right, is a blow up, or I should say gets blown up into this thing. Right, so this is a little tiny piece of the retina, which they're blowing up many thousands of times so that you can see this kind of schematic of the photoreceptors. So this is, the light is coming in this way. We have ganglion cells, we have bipolar cells, and then out here, we have photoreceptors, and actually where the business happens of photopigments responding to light is way deep here. So the light, as the schematic indicates, comes in here and then has to get past all this stuff, important stuff, but not particularly good for passing light through kind of stuff. So somehow this works. So the photons actually have to travel through here and reach these photochemicals here in order for the photoreceptors to do business. So I don't know why they built it backwards like that, but they did. So the light comes in, goes through all these layers of cells to get to the photoreceptors. I think that would be a good idea, but it is, and apparently it works really well. What else is to be seen here? So we have the fovea, which getting ahead of my thing here. All right. So anyway, let me back out of that. So that's the retina at this level. We'll talk about the retina more in a second. So we have photoreceptors that are connected to sensory neurons. Yeah, that's pretty okay. We have this fovea here at the center. So this is that place in your visual system where you get the best clarity and receptivity, right? So you have things that are happening. So if I'm looking here and I can still see things out in my visual field here, right? But if you hold up fingers, like I could guess at how many there were, but I'm guessing, right? And I kind of want to move my retina over there so I can foveate it, right? So your visual field has this center to it where things are crisp and clear, and like if you're reading, you want to be right there, right? And then it has the surround that kind of, it all feels like one big scene, right? You feel like you're kind of in this great big visual scene, and you are, but it's not equally crisp everywhere. So the fovea is that little focal area that allows you to be see super fine detail. And we'll say why that is. Okay, so the optic nerve is a sort of a cabling of the axon coming off of the ganglion cells, which are like a couple of processing steps down from the photoreceptors themselves. We'll see that in a little bit more detail too. All right, so they kind of get cabled together, and they form this thing that we call the optic nerve, and that heads out, essentially headed for visual processing in the brain. So where am I going here? That's good. Okay, so that's the first introduction, and you see that we have parts that we can say are about collecting and structuring the light, and then we have parts that are about transduction, and they're very very specialized, much more specialized than we've kind of hit on yet. Questions on any of that? Yes, go ahead.
Mentioned this earlier, but what does the ciliary body do, and like there's other like polaroid and scleron?
Yeah, don't worry about these guys too much. Yes, I mean you can look up what these guys are, right? This is kind of a hard shell, and this guy's kind of a softer shell. You know, if you get problems with them, they'll, you know, your eye doctor will be like, well, you know, you've got inflammation of your something. The ciliary body is controlling the muscles that connect to the lens.
Basically, bends the line.
Right, so it's yes, yeah, listen. Exactly so. Okay, other questions? Yeah.
What's the optic nerve connect to?
Well, we'll get to that, but it's going for a long run, right? So it's gonna go through some processing centers in midbrain, and then but eventually it's headed toward the occipital lobe. But yeah, there's a lot of debate about how much processing happens. You'll see in a moment that a lot happens like right at the retinal level, even before it leaves. So that's kind of interesting. But then there are also lots of other stages of it. Let's talk about the retina a little bit. So this is a more detailed blow up of the retina. And let me orient you here. So this is the surface of the retina, right? So in here would be the interior of the eyeball, right? And where the sun is. The sun actually isn't in the interior of your eyeball, but you kind of get the idea. That's where the light's going to be. And this is actually filled with a vitreous humor and an aqueous humor. The vitreous humor is viscous. The aqueous humor is turning over all the time and is more liquid-like. All right, but this is the sort of the surface inside the eyeball, right? Inside the chamber of the eye, right? So the surface is there, and this is meant to just show that there's a light source, and the light is coming this way. And then this very strange upside down kind of construction, at least as you might expect it to be. You might expect that that these guys, which are kind of down pathway cells, would be down here at the bottom, and that the light would be immediately in contact with the photoreceptors, but it's inverted. So the ganglion cells, which we'll get to a little bit of function in a bit, and the bipolar cells, which we won't really have to mention much again, are in between the photoreceptors, which are going to be these guys, and the light source. So it's perfectly fine and quite accurate to think about the photoreceptors being down at the bottom there, and the actual photochemicals, so to speak, perfectly fine way to say it, are down in here. Okay? But these guys all form like a network of interconnections that people who do vision find pretty fascinating. And there are well-known properties now of which ones are connected to which in broad strokes, right? Obviously, everybody's retina is different, and cells are constantly turning over. But there are kind of properties of the network that are understood. But you should think about these guys as forming both inhibitory and excitatory connections across the network. And that's part of what makes vision at the retinal level so fascinating, is that we haven't, you know, we're still in the retina, and we have like a whole interconnected network of neurons passing messages to each other, right? And it's still in your eye. Pretty remarkable. So the retina consists of 11 layers of cells. which includes the photoreceptors. There are 130 million photoreceptors approximately in each eye. So lots and lots, and not equally distributed, of course. There are about 1 million axons from the ganglion cells that lead out of each eye to form the optic nerve. The photoreceptors are like in a bath of sodium and potassium ions, which is really nice for them kind of quickly re-upping what they need to do, right? So they, once they change their neurotransmitter rates, they're very quickly like they have all the supplies necessary to be ready to go again. So that bath makes an awful lot of sense. So the photoreceptors, of course, which are labeled down here as rods and cones, and we'll get to that distinction in a second, contain photopigments, and these are compounds that have a protein and have a particular photosensitive compound that changes when photons of a particular frequency essentially impact them. And it's kind of all statistical and distributional, if you see what I mean. It's not like they're looking for just one. It's sort of like the probability of this photoreceptor firing is highest with photoreceptors in this frequency, or I'm sorry, photons in this frequency, and somewhat lower this other frequency. Right? And there could be combinations of frequency and so on and so forth. So it's so they're kind of each tuned, if you will, in that way. So the steps of transduction, that is photon striking, maybe lots of photon striking, but we can say one photon striking, I suppose, kind of go like this, right? So we have light that has made it all the way through here, strikes the photoreceptors, causes some changes down here. Those changes are in the photopigment itself, which then creates, for what for our purposes can be a chemical cascade, or it's a changing of a protein configuration that changes how the rate at which the neurotransmitter from that photoreceptor is released. So that's that chemical cascade, and it actually reduces the rate of neurotransmitter release. So, oddly, your visual system is, the photoreceptors are most active when it's dark, in the sense of releasing neurotransmitter. Right? So when it's dark, the photoreceptors are gone in terms of releasing neurotransmitter. When they reduce neurotransmitter, then the next guys in line here, which are bipolar cells, these guys, they fire. Okay? So it's odd, counterintuitive, but that's how it works. The bipolar cells, then, assuming that everything is kind of going to sum up nicely, the bipolar cells would then fire. That would stimulate the ganglion cells. The ganglion cells would then transmit down the optic nerve to the brain. Okay, so those are the broad stroke theoretical steps. Okay, so that's schematically how it works. It's interesting that there's this reduction rather than an increase in neurotransmitter release. There must be a reason for that. Maybe it is somehow makes it more sensitive. I'm not certain. I haven't heard it sort of definitively discussed. Questions on this? Okay. All right. So there are, as I've already kind of alluded to, two classes of photoreceptors. One of the important and major discoveries from psychology way back in the day, just on behavioral data, that people like to point out, is that they were able to discern that there were probably two classes of photoreceptor just from behavioral data. So people in psychology are always, they like to cling to these things because now things have gotten very, very technical. You can imagine in neuroscience. So when they ask questions about photoreceptors, no one's really asking questions about behavior so much anymore. It's mostly about retina on a slide kind of thing. But back in the day, they just had behavioral data, and they had this phenomenon that's called dark adaptation. We still have this phenomenon. And it's very simple. If we plunge ourselves into darkness, right, the room is suddenly dark. Initially, you can't see very much at all, right? But then after a few minutes, you start being sensitive to the very low level of light that's in the room, and you can start to see stuff, right? So you get this, you've been reading, maybe you got the light on, you turn off the light, you're going to bed, and it is dark in there. I remember this kid being like, oh no, it's too dark, I'm not gonna be able to sleep, I'm scared. No way. And then you'd be like, well, okay, I can see. So that. And then maybe it was worse this evening, right? But anyway, so that's the phenomenon. So when we go from a bright room, but into a dark room, you can't see it first, right? So we go like this. All right. And initially it's very bright. So if one moves that phenomenon into the lab, you can put people in the dark for an extended period of time and then test them after so many minutes in the dark for their threshold for light. You with me? It's very laborious, but you can imagine how it'd be done, right? So you're like, there you're the subject, you're plunged into darkness. After a minute has transpired, I measure your threshold for light by having very weak light come on, maybe a little bit stronger, and then maybe a little bit stronger. You know what I mean? And then at some point, say, yeah, I see it. Okay, so you do that. It's a bit of a mess, but it can be done. And it's not hard to do, it's just like tedious. So when you do this, what you get is a threshold value for each level of minutes in the dark. Okay? Where threshold means you need at least this much light to say, yes, I see it. Right? So lower thresholds mean that you're more sensitive. Right? It takes a little bit of light, my threshold is low. If it takes a lot of light, my threshold is high, and I can't see. Right? So sensibly, immediately after being plunged into the dark, your threshold from the light, your threshold is very high, and then it goes down, and it kind of starts to level off. And then after a particular amount of time, pretty much the same for everybody, it starts to go down again. So that was a mystery to people, and they were very interested in people. Decided that one explanation of that, not the only explanation, but one explanation, is that maybe there were two different types of receptors, right? So as I just said, so it improves for about 5 minutes, then it does this kind of leveling off thing, like it's going to level off, and then it starts improving. So this kink in the function, if you will, suggests that maybe what we're looking at are two functions laid on top of each other. One function for each type of receptor was their theory. Okay. So the first one, in theory, would change rapidly, okay, but kind of reach its maximum adaptation level rapidly as well. The second one would be, imagine this function extends all the way out here, would change very, very slowly at first, right? But then kind of keep changing afterwards, right? So it adapts more slowly, but adapts more ultimately. So these two functions together, sort of their minima together, right, would form this thing in theory. That makes sense? And that's what they got excited with. There are actually two functions here superimposed on each other behaviorally. And that's why we have this kind of weird function for dark adaptation. So the two functions suggested to them two systems, and ultimately bore out correctly that there were two different types of photoreceptors, which we distinguish by their shapes. Traditionally, there are rods, there are cones. The cones, in the case of dark adaptation, are doing that fast adaptation for you. And they are limited in what they can do adaptation-wise. But what they do, they do quickly. Rods are better at dark adaptation in the sense that they can ultimately give you a much lower threshold, but it takes them a while to do their business. That's why there was this kink in this function, and indeed rods and cones now are clearly anatomically different, functionally different, well understood. But it's one of the cool things about that. You know, these people were pretty smart to be able to know that that wasn't just like nothing. Figure out that there something was underlying them. So rods versus cones turns out to be a very important distinction for the visual system, and actually explains a lot of the functionality that the visual system has for us. Right? Not just dark adaptation. Because there are these two different, almost like sub-visual systems in a way, right? There's two visual systems that are let's think about that way. Two visual systems that are giving us this unified experience. Right? Very interesting way to go about things. We have this tremendous range of capability in terms of luminance, right? So when you're out in the bright sunlight, I mean, you are just being freaking bombarded with photons. I mean, absolutely bombarded. It's like 10 to the 17 photons per some tiny little area. It's just unbelievable. When you're in dim light, there's a tiny little bit relatively, right? It's like 20 orders of magnitude. And yet your visual system works across that whole thing. So you have one system that works pretty well in dim light, really well in dim light, to give it its credit. And we have another system that works very well in bright light. And from your perspective, it's all pretty much just vision. Right? So somehow these two systems have been merged into this one experience for us. So if you're not following this color coding here, so the stuff in orange is all about the rods, and the stuff in green is all about the cones. So we get the ability to see in dim light. We get really great sensitivity in the sense of low threshold, okay, from rods, and we get essentially like black and white vision, which you have. Right, there's that like time at dusk when things go from color, right? That's a very pretty time of night, right? And everything is nicely, oh, it's a sunset, and then suddenly everything's in black and white. Okay, or most things are in black and white. So that's this system shutting down and this system kind of taking over. Doesn't really shut down all the way, but it can't contribute very much. So the cones work in bright light. They give you really nice acuity, but not quite the sensitivity. All right, so acuity for us is going to be the ability to pick out fine detail, where sensitivity, as we're talking about it, is sensitivity to the presence or absence of light. So the cones are really good at acuity. When you want to see something in fine detail, you put your cones on there, which you actually do that because the cones are in the fovea, which we'll get to as well in a second. And it is the cones, but not the rods, that give you color vision. here is the rod story, pumped up a little bit. So the rods give us something called scotopic vision, which means low light vision. 25-cent word, scotopic. They are more plentiful than the rods, more plentiful than the cones. There are just literally more of them by quite a bit. They are distributed more or less equally throughout the retina, although not so much in the fovea. They have really nice sensitivity, as we just talked about, to light, but also to motion. So when things move, you have that like sudden attention grabbing feature of motion, right? Even something in the way out here in the corner of your visual field to get motion, right? Very powerful for us. That's from the rod system. And as we said, they have lower threshold in dark adaptation. All right, so that's the rods. The cones give us something we call photopic vision, which is like high light condition vision. They are relatively fewer in number, as you can kind of see here. There are some of them outside of the fovea, but mostly they're concentrated in the fovea. You have sort of an occasional member out in the other parts of the retina. But generally they're here, and this is meant to be the fovea here. And as I just said, they give us greater acuity, that clarity, that ability to discriminate detail. Okay, so there aren't, and this is weird, but true, there aren't any receptors where the optic nerve leaves the retina. Right, so because of the backwards way, right, you have photoreceptors down here, and then you have projections up to the surface. Well, then the axons, right? Imagine you're trying to wire this thing. The axons and the axons have to go out on the surface. Then eventually, of course, they have to make a cut back through the retina as a group, because that was designed as a group. They make a cut back through the retina, the nerve does, and that happens here at this place called the blind spot. So the blind spot, because of the architecture of the thing, right, for kind of spatial reasons, can't have any photoreceptors there because it's got cable. So it's like there's a cable running out, and everywhere else has photoreceptors, but you can't have it here because I actually have a cable. Okay, so that's what makes the blind spot, is the optic nerve leaving through the retina, right? And again, this is one of those things where you're like, well, that doesn't make any sense, because shouldn't the photoreceptors, right? Why would you put the cable out the back? But they didn't put the cable out the back. They put the cable out the front. Then it has to go back through the surface of the retina itself. Right? So there can't be any photoreceptors here because I got them. That makes sense? Yeah, it doesn't make sense from a design perspective. That's how it is. Okay, so there you don't have any photoreceptors, and yet, I don't know about you, but at least for me, I feel like I have continuous vision all the way through here, right? I don't have a blind spot that I am aware of, right? It's odd. You can demonstrate for yourself the blind spot. I'm sure your book has a demonstration of it. Essentially what you do is you usually it's the book, hold the book away from your nose and then slowly bring it towards yourself. They'll be slightly off. It's not in your fovea, right? So your fovea is going to have to stay there. The blind spot's going to be over here approximately. And as you move things towards yourself, at some point, whatever it is, it's like an X or something, is going to just disappear. And it's going to feel, it's not going to be clean and clear. It's it's gonna feel, as long as you keep the fovea here, it's gonna feel like, oh, the page just sort of absorbed that. You bring it a little closer and then it'll appear on the other side. You can demonstrate it for yourself, but in your everyday phenomenology, you don't feel like there's a blind spot. So, last little thing, contrasting rods and cones, and then we'll talk about. Oh wait, no, I don't know that we will. Briefly, we'll talk about a little bit of the beginning of the color vision story. So one other thing to know is that the ratio of cones, these guys, to bipolar cells is 1 to 1. Okay, so even though there are many, many fewer of them, many fewer of them, they actually are in 1 to 1 relationship with the bipolar cells. The rods are in a many to 1 relationship with the bipolar cells. So the cones can do that kind of detail because at the first step, at least, they're talking directly to an individual dedicated bipolar cell. The rods are essentially contributing in that first step to the bipolar cells, to many, right? So I've got 30 of them all talking to the same one. Well, obviously at that point, I've lost the discrimination amongst the bipolar cells that are talking. If I have 30 rods that are talking all at once, well, this one bipolar cell is like, well, I don't know, give me the majority opinion, right? And the discrimination amongst the rods is lost. So that's part of why rods are, like even in that first step, it's going to be clear that rods aren't going to be as finely tuned spatially as the cones. So that's one of like the network property details that people allude to. Oh, crap. So long-winded. All right. I'll just give you a hint and then we'll do it next time about color vision before we wrap things up. So one thing that completely mystified people, remember this is way back, right? So they didn't really know about the different types of cells. They were totally speculating. They were trying to figure out how on earth you could see color. So color is a perceptual phenomenon, right? It feels like it's part of the real world, but it's really you in interaction with that electromagnetic spectrum. It's your reaction to it and the combinations of light coming back to you, right? So it isn't like length or something. It's an experience somehow that is happening in interaction with your visual system. So the question was, how could you go from light to the experience of colors? So this very clever fellow, Helmholtz, who we've mentioned before, noted that any color can be produced by lights now, mixing lights together. Any color could be produced by some combination of blue, green, and red. So if you just have lights, you can mix those together, get any color in the whole spectrum. That's pretty interesting. And remember, that's just like, he's actually asking a question both about physics, colors that he's mixing, but then the other side of that equation isn't physics, it's perception of color, right? So what he's saying is, you have the experience of color when I mix together these three things. So I can, in other words, I make you experience this color by mixing together these. Right? So that's not like the real color. That's just the experience you're having. Okay. But from there, he's going to propose a theory. You know what's so frustrating about it? He's got to be right. Okay. So next time I'll tell you about how he's right.